linear algebra or calculus. One example, two ways of thinking, and you decide which one wins. Okay, let's consider this simple example which consists of these two linear equations. Now, the goal is to determine x and y so that both equations are satisfied simultaneously. So, how do we find x and y? Well, in calculus, we love functions. So we rewrite each of these two equations as a function by solving for y. For the first equation, we get this one. You know this kind of notation. On the left, there's only y, and on the right, there's something involving x. This is a linear function with slope minus 2/3. Instead of y, we often write f of x. It simply looks more like a function. So for a specific x, I get a value, f of x, or y, as a result, which I can represent here, for example, with a table of values. We can do the same thing for the second equation. Solve for y. Instead of y, let's write g of x, so we don't confuse it with the function we already called f. And voila, a nice linear function, this time with slope 5/4. Okay, what we also love to do in calculus is to draw functions. So let's do that here. On the left side, f of x, and on the right side, g of x. Each equation is therefore represented here by a function, more precisely by this line, on which its condition is satisfied. For example, on the left, if x equals -1, I can see that the function value f of x, which is my y, is 3. If x equals 2, the function value, so my y, is 1, and so on. So that both conditions are satisfied at the same time, the point has to lie on both lines simultaneously. That is exactly where they intersect. So we are looking for the intersection point of f and g. That is the x where the function values are equal. Let's write out the functions and solve for x. So we first get this, and ultimately x equals 2. Plugging this into one of the functions, we get y equals 1. So the intersection point is at x equals 2 and y equals 1. In calculus, you often see the solution as an equilibrium. This line is the path on which the first condition is happy. And this line is the path for the second condition. Only at the intersection point, there is no longer any conflict between the two conditions. In linear algebra, we don't turn the equations into such functions, but we can view this as one single system of linear equations. We can represent this as a matrix vector multiplication, because the first row on the matrix multiplied by the vector gives exactly 2x plus 3y, and together with the b component, that gives the full equation. And the second row of the matrix times the vector plus the b component results exactly in this equation. The matrix is usually denoted with a capital letter, for example A. And this vector here, the vector of unknowns, is generally written as x with an arrow over it, or simply in bold. The same goes for the result vector b. I'll stick with the arrow notation. Right, formally it's just another way of writing it, a matrix vector multiplication. And we have to find the vector x, that's correct. But conceptually, it's a completely different perspective. Because the cool thing here is the matrix A can be understood as a transformation. B arises by applying A to X. This matrix, for example, rotates every vector by 90 degrees counterclockwise. This matrix compresses a vector, meaning every vector becomes half as long, but its direction stays the same. The space is uniformly compressed toward the origin. And this matrix stretches and skews the vectors, or more precisely the plane. So the matrix A transforms the vector x. Every time, for example, when your character turns in the game, exactly this happens. Linear algebra. The graphics card fires the same matrix A at millions of vectors all at once. That is extremely efficient because computers are optimized for multiplying matrices. Okay, we are looking for the vector x, so that after the distortion by the matrix A, x lands exactly on the known vector B. So x is the vector in its original, undistorted state. It is the answer to the question, where did the journey start before the matrix A pushed the vector to the destination B? Or before my character in the game turned? You see, even though it just looks like a simple system of equations, conceptually, it is a completely different perspective that has incredibly many applications. Okay, to be honest, in our case, we are actually only interested in finding the vector x. The underlying transformation is not our main focus here. But now you know that from an algebraic point of view, there is a lot more going on. Alright, and how do we solve the system for the unknowns? Well, you've already done that many times. For example, with the Gaussian elimination. We write the system in augmented matrix form so we can systematically perform row operations. We eliminate x from the second row by subtracting the first row multiplied by 5 halves from the second row. Now we normalize the second row so that the coefficient of y becomes 1. Then we can read off y directly. With back substitution we now get x. We plug y equals 1 into the first equation and solve for x. And with that we have completely solved the linear system for our example here. You see, you've always been using a tool of linear algebra, it just was never mentioned in this context. The result also matches the intersection point of the lines from the calculus approach. You see, it's not really about how you calculate, but about how you think.